All right, in this lecture, let's discuss the concept of flux and also introduce surface integrals. So what we mean by flux is actually the amount, or is a measure of the amount of a vector field, say the electric field E, passing through a surface with an area vector A. And the area vector basically has a magnitude equal to the area of that surface with a direction perpendicular to the plane of that surface. So for example, we have, say, this electric field going here on the right, pointing to the right, and we have a surface A here, which is in this case presented perpendicularly, and so the flux is the amount of that vector field passing through that surface, and you can see kind of the maximum amount is passing through in this case. More specifically, the flux, which I will label by the uppercase Greek letter phi, we can write as the vector dot product between the vector field, in this case the electric field, as a vector dot product with the area vector A. And that dot product in magnitude, as you may recall, is the magnitude of the two vectors, E and A, for the electric field and the area, times the cosine of the angle between them. So in this case, they're completely parallel, so it would just be the product. Of course, if I had the area vector tilted a bit, as drawn here, if A was going down, then this small angle between the area vector direction and the electric field direction would be what I call theta in that case. All right. Okay. Let's consider now the flux through a closed surface, meaning a surface of a volume, as opposed to just this plane that's shown in the diagram there. And in doing so, I'm also going to break up that surface into a large number of small elements. Each will have an infinitesimal area we'll call delta A that are nearly flat, so we can approximate it by some sort of flat square or rectangle as we've shown in the upper right. By convention for a closed surface, meaning this volume, the area vector is always pointing away from the interior of the volume. So the area vector by convention always points out from a closed surface. So here is our surface here, rather complicated. It's kind of this heart-shaped or kidney bean-shaped surface. Our electric field, we see some field lines going here from left to right, and we want to work out the flux through this kind of complex shaped surface. So how are we going to do that? What we're going to do is we're going to break up the surface into a large number of smaller surfaces, basically by this grid you see overlaid on top of the outside surface of this shape. If you zoom in on any particular one, you can see one here onto the left, the area vector is pointing up and to the left. The electric field, of course, is moving toward the right. Theta, that angle theta, is that opening angle between the area vector and the electric field vector. Here's a similar but different area, one of the small squares here on the far right. Area vector is now pointing up and to the right. Electric field is to the right, and there's a different angle. So if we break up the surface that way, and we want to calculate the total flux through the surface, it's basically then just going to be this sum. The total flux, the amount of the vector field passing through this closed surface, can be thought of as the sum of the flux passing through every one of those surfaces. So I can have a sum from 1 to n of the n surfaces. And it's the vector dot product of the electric field with the area vector delta A. But let's go ahead and let n become very large. Let's let it go to infinity. But in doing so, that means we're shrinking the area of each small square or rectangle on that surface to become infinitesimally small. So it's going like 1 over infinity as n goes to infinity. In that case, instead of writing a sum, as you may not be surprised in calculus, we're going to replace that with an integral. So here I've written the flux phi in terms of this integral of E dot dA. E is the electric field again. It may depend where you are on the surface. And dA is an infinitesimal area vector. That's like my delta A, but I've shrunk it so small it's become infinitesimal. And I put an integral sign here in front, which means we're going to sum essentially over all those infinitesimal surfaces. And you might ask, well, why the circle and the integral sign? Well, that's kind of a reminder. This is a closed surface integral. We're integrating over the entire surface, front, back, left, right, around the whole surface area. It's a two-dimensional integral over a three-dimensional shape, in other words. And that circle is just indicating that we're integrating over the entire closed surface, not like just the top part or the bottom part. Okay, so that's just introducing flux as a surface integral of a field, vector field, with the area, infinitesimal area vector at a particular location along that surface, and then you integrate across that surface. Of course, that can be quite complicated for such a curved shape and for some arbitrary electric field, but we will solve some examples where we do that in more simple cases. For example, let's start with this most simplest of cases. Let's consider that our shape is a cube immersed in a constant electric field. And so my electric field is just some constant E naught pointing in the I hat direction, which means in the X direction. So here's my cube. I've got electric field pointing to it. And my cube is shown here, which has 6 faces, as you might know, for a cube. And I've drawn some axes here, X to the right, Y vertical, and Z pointing out of the screen. And so if we want to calculate the flux through this cube, actually we don't have to break it down to infinitesimal areas because we've got a nice symmetric situation here. So let's just do this with a summation where we'll do the flux through each face, and we'll add that together. So what we'll do is we'll take each face, say the top face, and we'll describe an area vector for that top face, similarly for a bottom face, and the front face, and back, and left and right. We'll give this cube a side length S, so that each area vector has a magnitude S squared, where S is that side length. Now, if I'm working out the flux through each face, there's some interesting cases here. If my electric field is exactly parallel to the x-axis, that means it's perfectly parallel to the top face of this cube, right? And so the area vector is pointing in the y direction, electric field in the x direction. Those are perpendicular to each other. That means that vector dot product is 0. There's no projection of E onto A, or vice versa, meaning theta was 90 degrees, cosine theta is 0. So since they're perpendicular, the flux to that top face is 0. There's no flux going through the surface. It doesn't have any component pointing into or out of that face. But it's not the only face, right? If that was true for the top, it must be true for the bottom. They're parallel. It's a cube. But look in front here. Let's look in 3 dimensions. The front face, the area vector is pointing out of the screen toward you. The electric field again is perpendicular to that. So that flux through that face is 0, and similarly behind, the back side is also going to give you 0 contribution. So there's really only 2 faces where you have flux that's not 0. The one on the left where the field's pointing in, and the one on the right where the field's pointing out. So that's what we have left. If we start with the right side, right, the electric field's pointing in the x direction, the area vector on the right side is pointing in the x direction. They're completely parallel. So the vector dot product is just going to be the magnitude of the product of their magnitudes. So that's E naught for my electric field, and the area vector had a magnitude S squared, so it's just E naught S squared for the flux through the right face. What about the left face? The left face here has electric field pointing in. The area vector would actually be pointing, and I can just draw it, pointing out to the left in the minus x direction. So that's a left. And so they're in opposite directions. That's a 180 degree difference in angle between directions. Cosine of 180 degrees, or cosine of pi, is -1. So in that case, the flux through that face is negative, but of the same magnitude as through the right face, E naught S squared. But because the area vector is pointing oppositely, it comes with a negative sign. So that means when I calculate the total flux over the entire closed surface, it's only those 2 sides that were non-zero, but in fact they cancel out, and the total flux through this cube is 0 when summed over all 6 faces. So for a constant electric field pointing in a particular direction, the flux through that closed surface comes out to be be 0. The flux going into the surface is balanced by the flux coming out of it. And now what's interesting, we did this for a simple case. We just took a cube. But what if I rotated the cube where one of the corners, say this corner here, was pointing toward the electric field? That's harder to solve algebraically, but it's the same thing. If it's a constant electric field, there's as much flux going in as there is going out. If it's a heart-shaped closed surface, the same thing is true. So for a constant electric field going through any arbitrary shaped surface, the total flux would be 0 because there's as much going in as there is going out through that closed surface. Okay, that ends this short lecture on flux and closed surfaces and also surface integrals.